general relativity step by step. Last time I defined this interval delta S squared, and I made the observation that if delta S squared was equal to 0 for one observer, it was 0 for all observers. What I want to do this, because the speed of light is constant, what I want to do this time is set up some coordinates x and t for a little person here, and then his friend in the spaceship, which is blue. There's the spaceship with a little person inside, and his spaceship's moving along. He's got his own different t bar, x bar system. What I want to do, go back to black, is show that delta S squared equals delta S bar squared. So the interval is the same for both the blue coordinate system and the black coordinate system. Okay, so how do I do that? Well, we've got this information here that if delta S squared equals 0, then they agree. So that's a good start. But now I want to look at non-zero values. So we've got delta S squared equals minus delta t squared plus delta x squared plus delta y squared plus delta z squared, and we've got delta S bar squared equals minus delta t bar squared plus delta x bar squared plus delta y bar squared plus delta z bar squared. So what I'm going to do is express delta S squared in terms of a quadratic form. It must be a quadratic form because everything's second order here. And I'm going to write it as just a matrix M, alpha, beta, let's say delta X alpha, delta X beta. And I want to figure out what these M's are, and hopefully we'll show that the identity is true. Actually, before I dive into the details of that, let me just express this in matrix form. Delta S squared equals this formula here. So I'm going to write it like, actually, I'll put that there, and then this here, and then this here. So that's delta t, delta x, delta y, delta z. See, I'm writing it out like a quadratic form. Delta t, delta x, delta y, delta z, and then that's minus 1, 2, 3, 0, plus 1, 0, 0, 0, 0, plus 1, 0, 0, 0, 0, plus 1. So all I've done here is take this formula here, take that formula there, and I've just rewritten it in nice, clean, clear matrix notation. I say, I keep on apologizing for this, but this is not strictly, this of course is my metric tensor here, metric tensor. It's not strictly correct because this is a column vector and this is a row vector, and they're both displacements which are on the same footing, not part of the dual spaces of one another. But nevertheless, I'm going to use matrix notation because it makes everything nice. So I've got my expression there for delta S squared. I'll go back to black, which is here. And now I'm going to write delta S bar squared, but I'm going to write that in terms of the unbarred coordinates. Delta x, no, I've got two x's there. Oops. That's a delta y and a delta z. It's the same thing. But it's going to be a general matrix. Actually, I won't close it off yet because I'm not sure how big I've got to make it. M00, 0, row 2, 0, 3, M10, M20, M30, M11, M12, M13, M21, M22, M23, M31, M32, M33 times delta t, delta x, delta tx, y, and z. Okay, so it's a bit of a mouthful. And of course, what I want to do, well, I want to find out what these m's are. I want to find out what these m's are for any displacement t, x, y, z, using the fact that both observers calculate the speed of light to be the same. I'm going to make the assumption here, let me just pinch in a little bit, m alpha beta equals m beta alpha. It says m is going to be a symmetric matrix. Because I'm a statistician, or at least that's my day job, I normally, when I say symmetric, my instinct is to say symmetric positive definite matrix. But of course, this matrix is not positive definite because it's got a negative element on the main diagonal, which means it cannot possibly be positive definite. I'm going to assume it's symmetric because basically I can interchange alpha and beta, and so every time I've got an alpha and beta I can swap them over, and I've got the symmetrically placed other term, and I may as well make them both the same. So it's no big deal making it symmetric. Okay, so that's what I'm going to do. I'm going to find, in the next screencast, I'm going to find M. And we'll see what it is, and I'll use that definition of M, or I'll use my physical reasoning to find out what the matrix M is, and then I will use that to show that the interval is in fact frame independent. I'm going to stop there because I don't want these screencasts to be too long. This one's already 6 minutes long and I don't like them being too long. So I'm going to stop here and do it in the next one. Stop.